Let's get on to, there's a couple of special events coming up. Yeah. There's the job fair coming up, and then this talk from YSYS, and then the Hacking Club will be back in a few weeks on Saturday, so those are things you might want to go to.
The same week.
Yeah, this is on Thursday, this on Saturday. Yeah, all right. And anyway, so here we are at 126, so it's time to talk about debugging. Yeah. Yeah? All right, so let's go here. All right, so I rearranged these things from the textbook because debugging is the easiest way to deal with assembly language. Disassembly is the hardest, so I moved it to later. So we're going to start with the debugger, which is much easier to use. And because you're running the program, it's a dynamic analysis, and therefore it's pretty easy and fun. So a disassembler shows the state of the program before execution begins, and then you have to imagine what would happen if you run the code. But in a debugger, you can run the code and stop it at certain points and just see what it does. So you can run code even if you don't bother to fully understand it. You can just run it to see what it does, and that makes it much easier. Ollie Debug is by far the most popular. The only problem with it is it's pretty old and only does 32-bit code. So if you want to do 64-bit code, you can use x64 debug, which is a free imitation of it. But if you really want to do a job, the thing to get used to is WinDebug. WinDebug is Microsoft's debugger, and it's the only debugger that can debug the kernel of Windows. So it is the most powerful. It is very strong. It is very hard to use. You pretty much have to write command line scripts to use it effectively. And you have to write them with these very terse commands with not obvious syntax. So we'll get there later. But we're going to start with Ollie, which is easy and popular. WinDebug is more powerful, but harder to use. Now, if you are a developer writing your own code in C++ or something, then you use a source code debugger. You connect the running code back to the lines of source code, and you don't read the assembly code directly, typically, which just makes it easier for you to find the mistakes in your code. But if you're a malware analyst, you don't have the source code, so you have to work from the assembly code. And you have to get a little bit better at reading assembly code and put breakpoints in there. Now, when an app crashes in Windows, Windows may offer to open this in the debugger, debug the program, and if it does, then it would launch the default debugger, which is typically WinDebug. And so when you have a crash, you can just say close the program and restart, which is what most users would do. But if you are trying to debug this program, then you would debug it, open it in the debugger, and maybe you can find out why it crashed. And if you have paid for a Windows tech support contract, you can take an image and you can send it to Microsoft, and they will analyze it at their end with WinDebug and get to the bottom of it. And this is the source of this giant repository called the Microsoft Knowledge Base, which is huge and has the most amazing stuff in it. When I taught Windows tech support, there was homework where you just solved it to the bottom of problems, and they have figured everything out. You will get this weird error message, and they will say, this is because you have this particular game installed and this particular network card, and we have written a special patch just for that machine here. And all that happens because that's somebody that paid for support. And then they actually had people at Windows get to the bottom of every crash. Anyway, so kernel versus user-land debugging. Yeah, this is chapter 8 here. Now in user mode debugging, which is what we're going to be doing, the code runs on the debugger runs on the same system as the code being analyzed, and you debug one executable. So the debugger itself is a user land process, so you're not messing with the kernel at all. All right, I see Voice Bahia has a question about CNIT 121. You should ask Richard. He's over in the other room right now teaching that class. But if you wait, I'll try and come up with an answer if you come back at 7:30. But I probably don't know the answer. Probably have to ask Richard. Anyway, all right. So the old way of now, if you want to debug the kernel of Windows, this is actually hard to understand how you could do it. Now you must do it in order to get bugs out of drivers and other kernel modules. But if you stop the kernel from running to analyze it, the machine is stopped. So you can't do anything. So the old way was you had to have two computers, and you connect them by cable. And the cable had to be an old 25-pin serial cable, which most of us have not even seen for 20 years. And the alternative was to pay $300 for an adapter to turn that into a USB. It was really pretty insane. So over the last few years, Microsoft tried to make this easier. They made it possible to connect by Ethernet between the two computers. But then came in Mark Rusinovich, the genius that wrote essentially all the tools we're using in this course. He figured out that you could make a crash dump and analyze the crash dump without stopping the kernel. And you could trick the debugger into analyzing the current state of the kernel without stopping it. And therefore, you can't run it and put in breakpoints, but you can put it in a debugger and see what it's doing on a single machine. And that's what we're going to do. So we're going to have some of the debug features available in WinDebug, but not breakpoints. And that way we can run on one machine without having to have two machines working together.
So then you will do both, user mode debugging and kernel mode.
Yes. But to be fair, you only can do limited kernel mode debugging. Yeah. However, it is so convenient we're doing it that way. Years ago, I used to actually have students set up two virtual machines, install virtual serial ports, connect them together, and then do the thing where one machine stops and the other machine controls it. And that was very buggy, very difficult to set up. And that's what you have to do if you really want to debug serious kernel problems. But for what we're doing, you can examine the kernel with just one machine, and it's much easier. So one thing you do have to do is you have to turn on debugging mode in your machine. It's a boot up option. You turn on this debugging mode. It's a special mode, and we're going to do it with PowerShell. We're with BCD edit, the command line command. We're not going to have to reboot the machine and go to advanced boot options, but that's another way to do it. And if you do this, then you have a break key, which is like Shift-Sys-Rec or something on your machine, and that key will cause the machine to have the blue screen of death. That's why you don't normally run machines in this mode. And by the way, it's the print screen key. So back in the old days, 10 years ago, my students would be in the lab trying to take a print screen and turn in their homework. And if this mode was turned on, the blue screen of death, and they're hosed. So that was inconvenient. Now we're using virtual machines and we're controlling this another way. But that's why you don't normally run things in debugging mode. Yeah.
No, I don't know if it is too early to ask this question.
No?
Because you showed that image, the previous one. I wanted to ask you if kernel mode is the same as privileged mode.
As what mode?
Privilege.
Previous mode?
Privilege. Privilege?
Privileged mode. Oh.
And
I think it is, yes. I think they call it privileged mode. It's ring 0 in the processor. Yeah.
So then I wanted to ask you, okay, so how these other modes fit into this dichotomy?
Yeah.
It is too early to talk about.
No, this is good. So now what's happening on your machine all the time, there are certain processes running in kernel mode. And they run before you log in, and they're at the top of like Process Explorer. And they have full control of the machine in the kernel. There are also a bunch of userland processes running. Not all the ones you launch are in userland. Now, in order to debug a userland program, all you need is to run another userland program. So that's fine. But if you want to debug the kernel, then your debugger has to reach into the kernel. And that is something that nothing can run in the kernel unless it's approved by Microsoft, essentially, like drivers and such. Most modern machines have driver signature enforcement. So it's a Microsoft program that goes in there. It's not OllyDebug. But when you run it, you're using a userland interface into it. But it is, in fact, reaching into the kernel. That was the old system. However, the new system from Rusinovich, you just execute a crash dump, and then you analyze the dump. So you sort of take a picture of the kernel and look at it in userland.
So I remain in userland.
Yeah. Everything we run is almost always in userland. Nothing directly touches into the kernel except the Windows API, and you don't interact with it interactively. Typically, you make one request, like change something, and it changes it, and then you're back. All you can run is API functions.
So then, just to be sure, then safe mode with command prompt, etc. Those are other modes. Those are more functional modes.
They're all boot up modes, but then you will use them from user mode. Now, all they do is reboot the machine with different restrictions. Safe mode turns off a bunch of unnecessary features like networking and most drivers to try to make your machine run because those are most likely the problem. And kernel and debugging mode turns on this debugging switch so you can send a special key press that will stop the kernel and therefore freeze the whole machine with the blue screen of death. And that is intended to be used when your machine is slaved to another machine through a cable, so that machine can examine the operating system. That's the idea. Yeah, we're going to use it. It's very good. These are very important questions. So anyway, all right, so the new way, like I say, LiveKD is the tool that Rakusinovich worked. LiveKD would just take an image of the kernel, and then you'd look at it. And it works pretty well. And now they've even built it into Microsoft's new debugger, where you don't even need to install the LiveKD tool. There's just an option to debug the current machine you're on. So let's try Kahoot.
Hey, I do that, that's good.
Yeah. Oh, well, maybe you got an old version somehow. Anyway, let's try the 8A.
So what is link? What was the last one? Link?
LiveKD.
LiveKD.
Yeah, but you don't really need it anymore. Now it's built into the debugger. The new version of WinDebug just has it built right in.
Oh,
okay. Yeah. So, all right. Yeah, this is what happens with most. Rakusinovich writes all these tools, and they're great, and it takes a few years for Microsoft to realize how great they are, and then they build them into Windows. So this is 126, all right. And we want chapter 8A. Let's see if sorting by something will do any good. All right, there we are, 8A. All right. Yep. All right, so which technique requires two computers connected together? Yep, that's kernel mode debugging in all its glory. All right, which technique is almost never used by malware analysis? Yep, of course, source code debugging would be nice, but you almost never have the source code. There have been a few cases where malware publishers actually accidentally left the source code in their published malware, but only the most amorous people would make that mistake. And there are some things that then turn public, like the Zeus exploit kit was used, and then somebody just dumped the source code and made it public. So that happens too. Right. So how do you display assembly code, but you can't run it? That's disassembly. Disassembly lets you see the code, but you can't run it. We'll get to that later. You do that with IDA Pro. All right, if a crash causes the blue screen of death, how can you debug it? The blue screen of death is caused by a crash in the kernel, so you can only diagnose it with kernel mode debugging. That's why you bother with these difficult procedures. All right. Go over here. So, all right, so to use your debugger, one simple way is launch the debugger, then open the program in the debugger, the way you would open a Microsoft Word document. Then it will load the program and stop before it runs any of the code. It just prepares it so you can look at it. However, another thing you can do is attach to a program that's already running, like a background service or something. Then it will pause it, and you'll catch it somewhere in the middle of its execution. Then you can step through the program step by step if you want to, one assembly language instruction at a time. The problem is you will have to step through thousands of instructions to get anything done, and it's easy to get lost in all those details. So here's code that decodes the string with XOR. So it's going to take some data from this address and move it into EDI. Then it's going to move in D, which is 13, into ECX. Then it's going to make a loop that XORs the data with a constant and increments. And this loop will loop back and forth. So there's a loop command in the assembly code, which loops, and it always loops and decreases ECX, and it will loop until ECX hits 0. Yeah.
When I was reading this specific paragraph,
Yeah.
the author, I mean, it seems to me that it was almost taken for granted that it can be recognized from watching at this picture that XOR has been used.
Yeah.
Where is the XOR?
Yeah, XOR right there. Yeah. That's it, good. And this is, you can see the key is 9C. So this is a simple XOR with a single byte key, which is a very limited kind of encoding or obfuscation. But that's the idea. So it just loads the words, XORs them, and then goes to the next one.
So basically the hexadecimal is turned into binary, XOR, then reconverted in hexadecimal. Yeah,
although in fact everything is all binary all along. As far as the processor, everything is binary. But yeah, for us, that's right. So this will XOR a block of bytes. Looks like 13 bytes somewhere. This is simple code to do that. And so you could single step through it, and then it will show you what's stored at this area of memory, and each loop you'll decode one more character, so you can see it change. So this is really quite handy. One thing you can do when you're lost is just step through the code and watch things like the register or the stack, and just see if something appears that's interesting. There's one way to find your way through code. All right, so now this is a really important one. If you have a call function, a call assembly command that's going to call a subroutine, you have a choice. You can step in. So if I execute, if I go through code like this and I single step, do a move, do an XOR, do an increment, okay, that's understandable. But if the next one is call a subroutine, how do I execute that? Do I run the call, do everything, and come back? Is that one step? Or do I take one step into the call and now do all the code inside the call? Now, the second one would seem more obvious, but it's usually a mistake because, remember, the way everything works, userland code is what the developer wrote, and all it's doing is making calls to the Windows API constantly. So if you step into, pretty soon you're going to be in the Windows API and then in the kernel. So if you were trying to debug something like malware, you're trying to find how the malware written by the author works. You probably don't want to be debugging how Microsoft Windows works inside. That would be a different task. So you don't want to step into the Microsoft Windows operating system code or the kernel and start worrying about what's going on inside there. That will be a big complicated problem, which is probably not relevant to your malware. So that's why you would probably step over. Step over would treat a call as one command, execute the call, do everything that call requests, then wait for return and call that one step. That's called step over. And sometimes you want to step over, sometimes you want to step into, but you need to understand what they are and make decisions about it. So then you can put in a breakpoint. A breakpoint, for example, here we go. This is a call that actually calls a calculated address. It calculates some number and puts it in ECX, then it finds some memory location, puts it in EAX, and goes there. So I can't tell where this is going, not until I reach this point. It's not a fixed address. So you put a breakpoint here, run to that point, and then look at EAX. Then you'll know what it's calling. So that's an issue. One of the many times you'd need to, it'd be helpful to have a breakpoint.
That would stop before calling.
Yeah, you put a breakpoint here, it will stop before it executes that command.
So basically, the result that I see is the end of the second line.
Right. Yeah, this line puts something in EAX, and I don't know what it is. So I put a breakpoint here, and then I can look and see what EAX was. Yep. And so here, we're going to calculate a file name and then create a file. So here we go again. It's going to add txt to the end. Here it's going to move txt someplace. Here it's going to do some kind of calculation, keeping track of the number of bytes written. It's going to have some kind of loop here, jump not 0 back to 20. So even without reading it in detail, I can see it's doing some kind of loop, doing something to things byte by byte here, like decoding it or something, then adding a txt at the end. Then down here, it's going to use that. Here's a file name. It's going to call create file. So this is what happens if you go in Notepad, for example, and you say save, and you give it a file name. This is the kind of code that would do that. You have to create the file name somewhere, like reading it from the keyboard. Then you have to call create file, and whenever you call a function, you have to push the arguments onto the stack. And all this is one call to create file. You're pushing all the arguments, some kind of template, some flags, some kind of creation flags, security attributes, share mode, desired access, file name, it's all this stuff. You push a bunch of parameters on the stack, then you call create file W. And so one of these parameters is the file name. So there was some kind of calculation to create the file name, so I could put a breakpoint here, or here, or here, because at that point the file name exists. And then I'll find the file name somewhere. So
How does the breakpoint visually present itself?
it gives you like a red, the letters turn red in the number. It's typically how you do it. Yeah.
And in terms of code, is that 0xCC, right?
Yes. And what it does, it replaces one byte with CC, exactly. Yep. Good. So that's what happens. So you put a breakpoint here, just let it run, and then you'll be able to see what the file name is. And therefore, you don't really need to read and understand all this, which is why I say debugging is easier than disassembly. All you need to do is spot the interesting places to stop. You don't really need to understand everything it does in between. And so here's what WinDebug looks like. It's pretty confusing. It's one of these Microsoft tools. I don't know why Microsoft does this. They take a tool, which is obviously a command line tool, and then they put it very loosely in a window just to drive you nuts. I mean, you have to type commands in this command line in the middle, and then the output shows up in this text screen, which scrolls away, and you have to keep scrolling back to find things. None of these buttons do anything very useful. So it really should just be a command line tool, in my opinion, but they forgot to ask my opinion when they designed this thing, so it's kind of screwy.
And the white part is the stack.
No, this is just whatever you put up there. You execute a command here. One will be to show the stack, one will be to show memory, one will be to show the registers. You execute a command and things will appear here. So here they put a breakpoint at create file W, and then they hit G to go. Now it hit the breakpoint, and every time it hits a breakpoint, it prints out the registers and stuff here. So EAX, EBX, ECX. So this is doing just what was happening on the previous slide. It put a breakpoint where it's going to create a file, and now it's going to call kernel-based create file W is here. So you find out, this is the command that dumps some memory starting at ESP +4, and there's the name, logfile.txt. So this is how you would do it in WinDebug.
But I can see that the stack is empty, right? Because EBX is 0.
That's ESP, no, ESP is here, 760A, 768. And
ESP and
EBP. ESP is 520 and EBP is 550. So the stack has 30 hex. Yep. Just like all. Yep. So this is what we've been doing in GDB. Anyway, all right. So for example, if you're sending encrypted data, using it anywhere in your program, this is why it's great. You don't need to figure out the encryption. You just need to figure out where it's going to actually send it, put a breakpoint there, and see the data that's decrypted. This is why I was just talking last night in the cryptography class, we're talking about AES and what strong cryptography means. And I say, even if your encryption is perfect, there's some point where you have the decrypted data, and you could just steal it at that point. with malware or a camera or something. That's why you have to understand encryption only provides a certain amount of protection. At some point, you have that decrypted data somewhere, and you could steal it from there. So you're going to see a breakpoint here. Again, same thing. You've got some calls here. Then there's a point where you call encrypt data. So you just put a breakpoint there. And at that point where you're about to encrypt it, you clearly have the unencrypted stuff. So read it there before it gets encrypted. Like down here, it's going to send the data over the network. Here, it's going to encrypt it. So you break it. Here's it going to get the data. So you wait for it to get the data, break it before it encrypts it, and then you can read it. Then it's going to encrypt it and send it. But if you were to use something like Wireshark, you'd only get the stuff that was sent, and you wouldn't be able to decrypt it. So that's the issue. All right, so here's Glorious Ollie debug. And we're going to use this a lot. And it just presents it all in a graphical way. More easy to use than WinDebug. You have the assembly code here. You have the registers here, EAX, EBX, ESP, and EBP, and all that stuff is there. You have the stack down here showing, and you have an area here where you can just dump any region of memory that's interesting in raw hex and in ASCII. So this turns out to be extremely useful, and this graphical layout is used by almost all modern debuggers, including ones. This turned out to be the handiest way to make a Windows debugger. And there's nothing like it in Linux. In Linux, you use a command line debugger, GDB, and there are attempts to make this convenience in Linux. None of them work very well. In my opinion, no Linux graphics tools are worth using. The command line is the way to use Linux. And most Linux users feel that way. So all the graphical tools don't work very well. You probably noticed if you've taken the hacking class, there's these graphical tools, and usually the graphics don't really work, and they don't respond very well and all that, because this isn't really where most Linux users live. They live in the command line. Anyway, so they have breakpoints. There's software, hardware, and conditional. And most of the time, you just use software. That is the most common normal breakpoint. Software execution breakpoint just changes the code by taking one byte and putting CC there instead. CC is the interrupt 3 that will stop it executing and come back to the debugger. So your debugger, which is written in some language like Python, just records what byte should be there and puts CC there instead. And when it hits the CC, when you continue, it will put the correct byte back in there and carry on. So that's a very simple process, and therefore you can have as many of those breakpoints as you want, and they'll serve the purpose of stopping every time it tries to run that instruction, and that's normally all you want. So here, for example, if you put a breakpoint here, here's the raw bytes. This says 55. 55 is push EBP. But when you put a breakpoint there, it's actually going to be CC. If you do a memory dump, you'll see it's really a CC there. The 55 is being stored in the debugger's memory to put back later, but while the breakpoint is there, it's really a CC. And that means you might get in trouble. There are some programs that do integrity checks. They will check the code and calculate a hash value or something, and your breakpoint is going to break that hash value. That's why this procedure is, perhaps you could call it a little bit sloppy. You actually modify the memory, but it's good enough for most purposes and most common breakpoint. So that's the issue. Sometimes, if your code verifies integrity, it won't run with this modified byte, so you don't want to use this kind of breakpoint. So then you use hardware execution breakpoints. These are the breakpoints built in the processor. There are special registers just for this. You can have up to 4 breakpoints, and when it hits that address, it will stop, and that's in the processor. Without changing the code, it will have a register that says stop when you hit this address. That's the idea.
Why we would switch from software to hardware breakpoints?
So you don't change the code at all.
For
Yeah. It's a more perfect way to do it. You are not modifying the code to put a breakpoint in. Your processor is just being told stop at this instruction. So this is technically the more perfect way to do it. It's just that you only have 4 such registers, and so normally you use the other technique. Right, and so running code, however, can change those registers, and they might interfere with the debugger. So if you wanted to write malware that would resist debugging, you could use integrity checking to stop the software breakpoints, and you could modify these registers to defeat the hardware breakpoints. So, it's like all of our techniques, they only go so far. A smart attacker could defeat any of our techniques, and that's why you have to realize this will happen to you. You run a tool and it doesn't work. It might not be that you're making a mistake. It might be that the malware is defeating your tool, and you might just have to go on and try some other tools. And then there are conditional breakpoints, and these are executed by the debugger software. They're not built into the processor. So suppose you have a loop that is run thousands of times, and you want to stop it under a certain condition. That might be after hundreds of iterations of the loop. Then, if you put a normal software breakpoint in there, it's going to break on every cycle of the loop, and you're going to have to keep hitting continue, continue, continue hundreds of times. So that's what this is for. You can set a condition, and it will break at this location, but only if a certain condition is true. And that's the issue. So it actually implements it as a software breakpoint CC, but then every time it breaks, it checks the condition, and if the condition is not true, then it automatically continues. So it does slow down quite a bit. It doesn't run at the blazing speed of assembly code. It jumps back out into your Python debugger to check the condition every time, but still it's faster than you having to hit a button every time. So these are not very commonly used, but it is an option to deal with the difficult situation where your breakpoint, you need to pass the breakpoint many times and stop only when a condition is true. There was an example in one of these textbooks, maybe this one, where you would put a break to deal with a rootkit, poison ivy, and it would be referring to some file, and you only wanted to stop when the size of that file was over a certain size. So anyway, that's the thing. So that's a conditional breakpoint. So let's take a look at another Kahoot. It's nice to have two screens. I can see there are no new comments in Twitch. That comment from Voice by Hia, but I don't understand it. Netacad is used in Cisco, not normally used in a computer forensics class. So they use Canvas, but they don't use Netacad in the forensics class. So that might be what's creating confusion there. Anyway. Competition's not too stiff tonight. There's only 3 players. They're all going to win. But anyway, we'll do it anyway in a spirit of reviewing. Yeah, maybe they fell asleep. That's life, yeah. You never know. All right. Well, we will carry on. All right, so what breakpoint uses interrupt 3? Yep, that's a software execution breakpoint. It will stop when you try to execute that line of code, the simplest case. All right. All right, what breakpoint might slow down your program? That's the conditional breakpoint, because you keep having to jump back to the debugger to decide whether you should be breaking. All right, what's the most common breakpoint? Software execution, that's really essentially the only one I've ever used, I think. It's good enough for almost every purpose. All right, and which one might miss important functionality? Yep, step over. You step over the function, you don't see what happens inside that function, and maybe that's important. All right, so Hacker Kitty. So let's carry on here. All right, so exceptions. Exceptions are how it gains control of a program. Breakpoints generate exceptions. A lot of things generate exceptions. The entire operating system of Windows is an interrupt-driven system. it waits for signals. Signals, network traffic is coming in, do something, the keyboard is being pressed to do something. It's all done by interrupts. So, except now, normally an interrupt is just a request for immediate service, but an exception means something has gone wrong. For example, when you hit Control-C, that generates an exception. When you turn off the power, that generates an exception. Say, you better shut down the machine. It doesn't just break the connection to the power unit. It sends a signal to the operating system saying, please perform an orderly shutdown. So other things do that too. Invalid memory access. If your program tries to read or write to memory that is not allocated for that purpose, that's invalid. Division by 0. If userland mode tries to execute a kernel mode command, that's another exception, privilege exception. You're trying to do something you don't have the privilege to do. So when the first exception happens while a debugger is attached, the program stops executing and it passes control to the debugger saying, well, is this a breakpoint? Maybe nothing's wrong. Maybe you want to handle it. The debugger can handle the exception, which is what it will do if it's a breakpoint, saying, okay, I'll take care of it. Or it can return it to the program saying, no, I'm not going to handle it. This is a real crash. You go and handle it. And then the program will see if the developer prepared for this. If they prepared an exception handler, maybe they can handle it, maybe not. That's the second chance. So you pass it back to the program, and then the program does whatever it's programmed to do with the exception. And that means in malware analysis, you can typically ignore first chance exceptions, but second chance exceptions might mean something crashed about the malware. And as I mentioned before about shellcode, in the exploit development class I was talking about that, there's typically no error handling in malware, as you would imagine. It's small as possible. It's not intended to be user-friendly. So if something is wrong, it will just crash. For example, if it expects a different version of Windows or a different network card or something, if anything is not working, it will probably just crash. And this often means that you're in trouble because as an analyst, you're running in a virtual machine and your virtual machine has not simulated the expected environment well enough. So the malware is not going to run. And this happens all the time in Android. If you want to analyze Android malware, you have to buy Android hardware. All the malware, what I've been told, is too smart to run in a virtual device. It notices it's in a virtual device and refuses to run.
Okay, if I don't have analysis code, so I caught this bug, this malware.
Yeah.
The environment is not friendly.
Yeah.
Does it mean that the malware won't hurt me?
Well, it might and it might not. It means it will have some kind of error, and the error may or may not completely stop it. It might do some harm before you hit the error. And this happens all the time. There's a lot of malware that goes and infects millions of machines, and when you analyze it, you find it has various bugs. Like often, there's malware that in fact crashes and forgets to ever phone home to get commands. But it messes up your machine on the way, because usually if they write it sloppily, it messes with your operating system and makes a mess of it. So it may do some damage, even if it does not have all the functionality working, just like any other, All right. And essentially, the malware samples we're using in this course are like that. They don't do much harm, but they do a little harm, like making it automatically restart or something. So int3 is the common one, software breakpoint. Single stepping. You can single step through one instruction, and it does that by just setting another breakpoint at every instruction. There's a register flag you can set in the processor that will automatically stop after every instruction. That's another way to do it. And then I mentioned the most common one is memory access violation. You tried to read, write, or execute some memory location that is not reserved for that purpose, for this program, so you don't have the privilege of doing that, and that's an exception. Like I say, having to execute ring 0 instructions from ring 3 is another privilege exception. And there's a whole list of exceptions online. You can see them all.
That link doesn't work.
What? Oh, okay, maybe it's down. That's really old. I mean, it's in the hardware. Yeah, thanks for telling me. That happens. That's link rot. Every year, like 10% of.
I was curious to get the list of exceptions.
Yeah, you'd have to Google for it. Yeah. All right. So you can skip a function. These are modifying execution. You can do other things besides a breakpoint. You can change things. You could change the value of a register. You can even change the value of EIP and jump to other code. That's the whole point. You can modify it in various ways. You could avoid a function call by setting a breakpoint at the call, then changing the instruction pointer to go after it. So it never calls that function. Now, this might break something because later on it might notice that whatever was supposed to happen there didn't happen. But anyway, that's the point. You're in complete control in a debugger. You can test a function. You could start at the beginning of a function and load the parameters on the stack yourself and run the function without having to bother writing a wrapper. All right, so in practice, with a real virus, for example, this is extremely common. People write malware because they are nation-state actors or because they are Russian. The Russians, the government, supports hackers hacking Americans. They will protect you. They will let you do it. They will not punish you. They will even warn you when Americans coming in trying to arrest you. But if you attack Russians, they will lock you up. So it is typical in Russian malware that it checks the language of your machine, and if it's Russian, it won't attack you because they don't want to go to jail. And the Russian government does not care if they attack other people. And the same thing's true of Chinese hackers and such. So often it will do this, check the language and only attack you. So this one, if it's Chinese, it will do nothing. If it's English, it'll just pop up a box. But if it's Japanese or Indonesian, then it will destroy the hard drive. So that was the purpose of this one. It's quite common. It targets certain locations. So the assembly code will be here. This is the API call to find out the location I'm in. And it sends me a code for the location. So then I check for various values. 409 is English, 411 is Japanese, 421 is Indonesian, C04 is Chinese. So if you're an American trying to analyze this on an English machine, you aren't going to get the malicious behavior. So you would put a breakpoint here when you come back and change the return value to Japanese. So now the malware will think it's in Japan and do the bad thing. That's the sort of thing you might do. All right, so let's try another Kahoot. All right.
So, but it has to detect the language before getting into action.
Right.
And so basically, pointing the pointer before the language kicks in.
Well, you let it run the language detection routine, and then you change the answer afterwards.
And change the...
Yeah, because it returns a code number to tell you what language it is.
Right.
So you put a breakpoint afterwards and change that code number back. So it thinks that code number that returned from the routine is different.
Okay, because I understood something. The book says, okay, you want to run the machine with the Japanese language.
Yeah.
Because you have to analyze what kind of damages could be done.
Yeah.
And then it explains exactly what you
Yeah.
just said.
So I mean, typically what you do, the rule is return values always come in EAX. When in like C language you say return to, it puts that in EAX.
Yeah.
So when you call this, when it comes back, EAX contains the result. So I would put a breakpoint here and then change EAX. And now it will think that that returned a different value.
Yeah, exactly.
That's an easy way to trick it. Yeah. Good? Yeah. Good? You know, that would be the best procedure because then it will most perfectly simulate being in Japan. If I just didn't even call the routine at all, it might notice something else that happened. This is one that puzzles me. It thinks I'm driving. There's some kind of defect in the iPhone system. My iPhone is in my pocket. I'm not driving. It thinks I'm moving. Anyway. My phone is kind of broken. That's probably it. I dropped it and it's imperfectly fixed. It's probably triggering a sensor. Yeah. All right, so which one of these handles exceptions during normal execution? Running in a debugger. That's what this means. So if you're not running in a debugger, that's what the exception handler does. That's the code written by the developer. And what this means in Python, for example, is instead of executing a command, you do try to execute this command and except, if there's an exception, do this. That's the exception handler. So this is what normal happens when you're just running software. All right, that was a little confusing, that one. All right, anyway, so which exception doesn't stop code execution and can usually be ignored? In a debugger, I should have said. First chance exception, yeah. All right. All right, so ring 3 process tries to access hardware directly. What will happen? That's a privilege violation. Only the kernel can do that. You're not allowed to do that. All right. So, I'm going to stop this recording.